All right, guys. I think this is where we left off. If not, we've already talked about all this stuff. I am pretty sure. Initializing the variable is how you give it a starting value. In Python, every time you first use a variable, you're initializing it because you can't declare the variable without sticking a value. In other languages, you can. Like this. You could, in another language, say string your name. Leave it like that, and then you have a variable named your name that you could use later. You can put Janita in it. Or you can just stick a value in it right when you create it, like that. The idea of declaring a variable without putting a value in it is like we did when we did the declaration section, if you remember that, and we just gave everything a value of 0. Not necessary. You can create your variables on the fly as you run along, right? You know, put some variables here, put some more variables down in the middle, whatever. So initializing it is the first time you give it a value. Don't have to use that term. You could just say, you know, assigning a value to it. I think I would use the term initializing it if I was doing something like giving it a value of 0 so I could start adding things to it, right? That really is a starting value, right? When you ask for somebody's name, it doesn't seem so much like initializing it to me. It seems just like putting a value in it, but it is technically initializing it. In the languages that let you declare a variable like this, if that was the end and you didn't have that, it holds what's called a garbage value. Doesn't have any valid data in it. So you have to use it. You have to put some data in it before you can use it. Not a problem for us. Every time we declare a variable, we stick a valid value in it. So we don't really care about garbage. So the variables have to have a value in it before they can be used in the program. So a named constant is a variable that we just put in caps to indicate that the program's not supposed to change it later. Like a math constant, or if once you put a value in tax amount, it's not supposed to be changed. Give it a good name. If you give it a good name, then it's easy to read the code and figure out what's going on here. You want to avoid magic numbers. A magic number would be if we did something like this, right? Right, we didn't know what this tax amount is. Well, they use 0.6 in their example is. You know, we're reading the code. We don't really know where that came. Maybe we have 0.06 strewn throughout the code, throughout the project. If we put it in a constant, like they had here, then you'd only have to change it one place, right? You have your constant up here at the top of the code, you know, and you set it equal to 0.06. And then every time you need that, you just put it, you know, where you need it. That way, if it needs to change, you only have to change it in one place. So arithmetic, we know how to do arithmetic. The rules of precedence, what happens first when you're doing some math. Pretty dang sure we covered this, but not going to give it too short a shrift. Nothing wrong with hitting it a second time. You also learned it in junior high or something like that. So if you have this expression, I have no idea what lecture we're on G. If you have this expression, a is equal to 1 plus 2 times 3 plus 4. All right. Here's not how it's solved. You don't add 1 and 2 to get 3, and then multiply that by 3 to get 9, and then add 4 to it to get 13. Right? It's not solved like that. Instead, multiplication happens first. So it's going to be 1 plus 6, which is 7, plus 4 is 11. Very important that that gets solved in the correct order. So if you really did want this to happen first, you'd have to do that, right? That would force this part to get done first. So good old, please excuse my dear Aunt Sally. PEMDAS. Parentheses for, why don't I just open a quote, right? Parentheses, exponents, then multiplication and division, also floor division and modulus. We didn't learn floor division and modulus in junior high, so nobody added letters, you know, to the mnemonic to remember that. And then addition and subtraction. So if you have this expression, the interest expression that we looked at last time, I think we did. Yeah, we did. Compound interest. No, go back. Show me the image. Like that. If you want to implement this, you have to be pretty careful. For one thing, you can't leave out the asterisks. So you have to make it p times. You have to put the parentheses in because you can't do p times 1 plus r over n without the parentheses, because the multiplication would happen and then the addition would happen. And then lastly, the nt, you need both an asterisk there, and you better have quotes around it. Why? Because if we had, and I know this is a slight rehash, if we had a is equal to, why is that 1 times? Oh, it's p times. Okay. If we had p times parentheses 1 plus r over n to the power of nt, what's wrong with that? Compared to that. There's a serious problem. There's a serious difference between that and that. What's the difference? Besides that, I may have put an uppercase letter where I wasn't supposed to, and that's not supposed to be 4 over n. I missed. That's an R. Come on, guys. Somebody look at the screen and tell me.
You got the division in with the addition.
Right, that's okay. This is okay because multiplication and division happen first, just like we would expect from that formula. So that one's not a problem. Did I hear that we need to put parentheses around that? That's correct. Why? Because exponents get done before anything else. So it would take this, raise it to the power of n, and then when all that was done, it'd multiply by t. It's not supposed to be multiplied by t. It's supposed to be raised to the power of t. So you'd have to put parentheses around it. The act of expressing a formula as a computer statement is known as composition. We know what an int is. It's a whole number. If you do, this statement is so completely wrong that I want to throw a book at the author of the PowerPoint. Well, I guess it's not wrong for every other language, but it's wrong for Python. I have a Python book that teaches the same thing, a pure Python book in another class, a scripting class, and it says the same thing, which is not true. What this is saying is if you divide 4 by 3 and they're both whole numbers, you're going to get the answer of 1 rather than 1.333. That's not true for Python. In Python, if you divide 4 by 3, you get 1.33333, right? Works the way human brains work. So that's good news. We have mentioned modulus, have we not? If we did this, A is equal to 1 mod modulus 2 or 3 mod 2. What does that equal? Feel free to say no. We haven't covered modulus, you fool. All right, we'll do it again. Okay, so floor division means you round down. So if we did A is equal to 3 floor divide, or integer division, floor divide by 2. 3 divided by 2 is 1.5, but you round it down, and that's 1. So what was the leftover? 3 divided by 2 was 1, but there was a leftover. And don't say 0.5, right? 2 goes into 3 times. 2 goes into 3 how many times?
2.
No, that would be 4. 2 goes into 3 how many times? 1. And then what's left? 1. Exactly. So 3 mod 2 is equal to 1. That's the remainder. How about A is equal to 6? I'm going to use the symbol for floor division. That's a symbol for floor division. 6 divided by 2. 6 floor divide 2. How many times does 2 go into 6?
3 times.
Yeah, goes 3 times. And what was left over? So if we do A is equal to 3, this is the symbol for modulus. How many, when 2 went into 6, it went in evenly, right? 2 goes into 6 3 times with no remainder. Modulus 10. 19 modulus 10. 10 goes into 19 one time. What's the remainder?
No.
Yeah. Y'all getting it? I should probably make a worksheet and make y'all fill it out. I'll consider that at the end of class if I allocate enough time for homework. I mean, when making homework. So, floor division is this symbol. It means divide and round down. The term round down is the loosey-goosey term for it because people think that, well, we're rounding it. Maybe we ought to round up. Like, what if it was 1.9? No, it drops. It goes always down, and the computer term for that is truncate. Truncate means to chop it off. If you take a snake and you truncate its tail, then it'd be pretty unhappy. It doesn't have a tail anymore. Isn't a whole snake a tail? Head, tail? No, I'm kidding. And then modulus is a percent symbol, which means remainder. Or divide and get remainder. Remainder after that. Right. I'm going to delete that part and just put remainder. What can you use modulus for? Say you want to calculate feet and inches. There's 12 inches in a foot. Something is 40 inches long or 399 inches long. We want to find out how many feet it is and how many inches there are. So, INPER, foot, excuse me, I'm making it look like a constant because there's always 12 feet in an inch. Excuse me, that's wrong. There's always 12 inches in a foot. Shouldn't change, making it a constant. All right, now we're going to ask the user for some inches. But I'm going to just hard code it, right? Because every time we run this program for the next 40 minutes, we'll have to be typing something. So inches is equal to 432. I hope that's not an even number. I'm going to make it a non-even number. Absolutely sure it's not an even number. 437. All right. So feet is equal to 437 floor divide by 12. So floor divide, IN underscore PER underscore foot. And then the inches, or I could just say IN, but nope, that's orange. I don't want to do that. Inches equals, wait, why did I say 437? We have that in a variable. Please correct this line. Correct it along with me. That should be the word inches. I was about to use it as a magic number. It is a magic number. We should be, asking the user for it, but whatever. And then inches equals inches modulus inches per foot. Firstly, I'm going to pretend that this is 13. I'm going to put a comment here and then I'm going to delete the comment. But if it was 13, 13 floor divide by 12 is 1. That's true. 13 inches is 1 foot, but it's a little more. And then if this was 13 modulus 12, then 12 went into 13 one time with a remainder of what? Right, so it would be 1 foot 1 inch. Now I'm going to delete that because I actually want to watch what it does. Lecture G. Ha! What did I do wrong? I didn't print it out. That's dumb. Let's print it out. Print, quote, feet equals, end quote, comma, feet, comma, quote, and then some spaces, or maybe even a tab. I'm just going to put some spaces. Inches equals, end quote, comma, inches, end parentheses. Now we find out what 437 inches is in feet. 36 feet, 5 inches. If you happen to know your height in inches, just fill that in. I'm going to pretend that I'm 70 inches tall. I have no idea. Maybe right. Right. That's about right. Right for me. Seems to be working. So, you can use floor division and modulus to convert units. Right, we could do pounds to ounces the same way. We could do meters to centimeters the same way. The difference between doing this is that previously, if we did pounds to ounces, we didn't mind, or vice versa, if we did ounces to pounds, we didn't mind printing 3.72 pounds, right? Or that a certain number of centimeters was equal to 5.43 meters, right? We didn't mind using a decimal. Decimals are great most of the time, but if you had to, right, you could do it that way. You can convert dollars to cents that way if you wanted to. I don't know why I'm... Okay, I'm going to get rid of these triple quotes here so that I can just keep typing comments. So like the above example, you could convert pennies to dollars and cents, or dollars and pennies. Except you wouldn't use 12, would you? You'd use 100. You'd make a different constant, right? Pennies per dollar. Or I don't care if you just use the number 100, but sticking at a constant would be all cool and stuff. You know, it'd be good programming style. Anybody have a syntax error yet? All good? So modules. Understanding the advantages of modularization. The idea of modules is making functions. Functions and modules are the same term. It's breaking down the problem. I'm going to give you some dumb examples. I always start off with the dumb examples. So define sing, parentheses in parentheses, print a wop bop a loop bop. We're doing Little Richard now. Print parentheses wop bam boop. All right, that's a cool song, right? I'm going to stick a return statement on it. All right, define hum. After we're done singing, we don't know the rest of the words, so we're going to start humming. Print parentheses. Print quote la-dee. Right there. Now we've hummed. Told you it was a silly example. Okay, so we're going to sing parentheses, and then we're going to hum parentheses, and then that song is stuck in our head, so we're going to sing again, and we're going to sing again, and we're going to hum again. What's it going to do? As it's cruising down, this is after the, you know, the feet and inches bit. It's going to hit this define statement. And it's going to define this function, this module, and it's going to hit this define statement. If I had this code gone, if I didn't have these calls to it, I'm going to cut them temporarily. You don't need to do this. All right. Well, dadgummit, it didn't print my song. It didn't hum. The reason why is it defined it, but it didn't use it. Like me drawing a map to Walmart. I drew a map to Walmart. That doesn't do me a darn bit of good, right? I just have a map. I have to follow the map, or I have to give you the map and tell you to go do it. Just because I define something doesn't mean it's going to do anything. It doesn't do anything until I call it. So that's why I have sing, hum, sing, sing, hum. So what it's going to do is it's going to cruise past the definitions. They're in memory now. So then I can call sing. It'll jump up here. It'll do that, and it'll return. Now it's ready for humming. It'll jump up here. It'll do that, it'll come back. Now it's ready to do the next one. Sing jumps back up here, does those two things, comes back. Sing again. Jumps back up here, does those two things, comes back. And then lastly, before we forget about the song, we hum. Jumps up here, it hums 2 lines, and then it comes back. So now when I run it, I'm going to see a whole bunch of output. Just to make the output easier to read, I'm going to put a \n here to go to the new line. And a \n here. It's just going to make the output prettier. It doesn't change the way it works. It just makes it prettier. The \/ is above the one above the enter key, not below the question mark. All right, and there's our humming and our singing. Can I make it hide the title bar, the doc? Taskbar settings. Okay. Give myself a little bit more room. All right. So we see it sang just like that. It hummed. It sang again. It sang again. And then it hummed again. All right, now I'm going to quickly draw this code as a flowchart. You don't need to do this with me because we're probably going to flowchart a better non-silly example. So let me just whip this one off, and then you can work with me on it. To define a function, you use the same thing. Use the oval. Although the textbook gives it a different name. It calls it a century rather than a terminator. I don't care if you call it a terminator or a century. Everybody else on the planet calls it a terminator. The book's a little bit different. Anyways, for a function, you don't put start. Instead, you give it the name of the function. Strictly speaking, you don't have to put the DEF keyword there, but I like the DEF keyword because that's what we use in our code, and we're allowed to customize the way we do flowcharting a little bit. Okay, so there. Define sing. Looks just like our module definition. The book would say that we could leave DEF off. And then we come down here and we do a print, quote, or output, whatever, right? Oh, wop, bop, etc., right? And then return. Now humming, pretty much the same thing. I need a start, but again it has to have the name of it. So define hum, parentheses in parentheses. The parentheses in parentheses means that it's a function. You put the parentheses there when you define it, and you put the parentheses there when you call it. All right, now it's going to come down here and it's going to print something else. Right, it's going to print humming. Print. Right, whatever. And then it's going to return. All right, now we're going to show what the main part of the code is. The main part of the code is the unintended code. What you typically do is you put the functions up at the top. This code, Python doesn't make you do that. You can define your functions right there. But if I was going to do this code and send it to somebody else and I wanted to look professional, I would cut that stuff. I would scroll up to the top and paste it. I'm not going to do that because I like it being real close to where it's being called just for the notes, right? Maybe I'll put a comment there, though. My comment's going to be define two functions, and then usually functions are defined at the top of the code. Okay. Where was I? I was drawing this. Okay, we sing, hum, sing, sing, hum. So out over here, I need to write some main code that does that. My main code does begin with start. So I'm going to draw a start block, and I'm going to call sing first. I'm using a special block though. Notice it's got the bars on the side. Sing, and then it's got a hum, and we'll do another one of these for real that I'm going to want you to type along with if you want. And then another sing, and then another sing, and then a hum. Why don't I just copy and paste? Right. Another sing. Another sing. I would be making these blocks smaller usually. Try to get it all on one screen. And then a hum. And then I stop. Functions, you put DEF and the definition name, and then the return. Main code begins with start, ends with stop. Now I'm going to totally cheat here, and I'm just going to draw a line from here going down to here, and then I'm going to set these things. I'm going to bring them up to the front, just like you were using a drawing program. So arrange, bring to front, arrange, bring to front, right? And that's kind of cheating because we don't have the little arrowheads every spot, but quick and dirty is sometimes okay. So there's our code. I'm going to do something nasty looking. No, I won't. All right. I'm zooming way out because you get the idea. This is calling sing. This is calling hum. This is calling sing. This is calling sing. This is calling hum. Now you might be tempted, and the first time the book shows this concept, it shows an arrow going to the beginning of the module and then coming back. Yeah, that's the way it works. That's the logic, but I don't feel like doing that every single time. Watch what happens when I start doing it every single time. Right? It starts getting messy looking. Right? You can be sure that I'm going to undo this real fast. Right? Okay. Right, that's beginning to look real stupid. The mere fact that these are rectangles with bars. And by the way, when the book shows it, it uses horizontal rather than vertical bars. Doesn't matter. It shows one bar rather than two. Doesn't matter. The book chose one symbol for it. There's no horizontal bar here. There's something that kind of looks like that, but it's also got a vertical bar. This one's the closest. This one is called a predefined process. Predefined, right? We defined it. We defined it up somewhere else. Okay, now to make this code easier to follow, this is my own personal quirk, but I like to color code my functions. I'm going to make the sing block. I'm going to use the paint bucket to fill it maybe pale blue. I'm going to make the hum block maybe a pale orange or yellow. And then everywhere there's a sing, I'm going to fill it with pale blue, right? And some of y'all already are colorizing your things, and I'm not telling you, oops, that one was supposed to be orange because it's calling hum, right? And then another sing. Dadgummit. I'm talking while I'm doing this and I'm messing it up. All the sings are supposed to be blue. All the sings are supposed to be blue. Let me stop talking while I do that. Make sure it's right. All right. Now I'm good to go. Right? Even though you can't read the words, you could tell, right? Oh, I need to get rid of that line. I told you I wasn't going to do lines from the calls. When you call a function, when you have something that invokes a function, it's called calling it. That's the colloquial term. Invoking, if we want to get all fancy. The book, I think, uses both terms. I'll usually say call. Simpler, right? So call sing, it runs over here, comes back. Call hum, runs over here and comes back. Call sing, right, jumps back over here, comes back. That is how you draw functions and how you do function calls. We'll do a real example in a minute. Okay, more in a minute, but yeah. Here's another example I came up with. It's total garbage. It doesn't mean anything. But you can tell what it's doing, right? It does something else, and then it makes a function call. The function call would jump over here. And while it's running down, oh, well, what do you know? There's a function call right inside this function. And yes, functions can call functions. Modules can call modules. So it bops up here. It does this stuff, comes all the way down there. Right? Then it comes back there. Just like there was an arrow going from here and then coming back to here. Oops. Right, just like that. Imaginary lines. Those lines aren't there. And then this is going over here, right? And then from the return, it's coming back, right? Just like that. And then down here, it does the same thing for whatever purpose. Like I said, this is garbage. It's not a real program. But you can tell. You can tell what are functions. You can tell when we're calling the modules. That's why I like color coding it. You don't have to do that. Makes it easier to see, in my opinion. If I give you a flowchart that I want you to implement as code, I will probably color code it like that just to make it easier. So what about pseudocode? What should it look like when we do pseudocode of our singing and our humming? All right, not Pseudocode. Bear with me. I'm going to open, I think, Notepad to do this. You don't need to do that. I just want to have both bits on the same screen, right? And I can slap that one over there and be ready to go. Why don't we look at the book? All right. We're jumping ahead several chapters, several pages, blah, 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 blah. Can we get to the real stuff? Please? Oh, for Pete's sake. I know it shows it, and I am just apparently going too fast to spot it. Okay. Here's how you define a module in pseudocode, or how I want you to do it. The book's going to show it a little bit differently. I don't care if you do it a little bit differently. I think the book would just do it like that without the DEF in front of it. I like seeing the word def. Define. Or, you know, you could put the word function there. Or you could put the word module there, right? Pseudocode is kind of loosey-goosey. But anyways, it's supposed to output something, right? A wop, bop, whatever. I'm going to make that a whop, bop, whatever. You get the idea. I know that that's a racially charged term. And so anyways. And then whop, whop, bam, boom, etc. Right? The book would show the return statement being like that. I'm going to go back and add the DEF keyword there. All right, now to do the same thing for hum. Define hum, parentheses in parentheses. And I'm going to copy and paste this into my real code in just a minute. Output, quote, output, la, di, and then a return. Now we're ready for our main code. The main code is the unintended code over here. So our main code, according to pseudocode, starts with the word start. And then we call sing, and we call hum, We call sing, whatever. That's about an, and then a hum, or another sing, and then another hum. And then we have stop. That's pretty good pseudocode for what's going on. There's something that I don't particularly enjoy about the way this flowchart is set up. Excuse me, this pseudocode is set up. What's that? The word return here is indented, and it's not indented over here. If I was not teaching to the book, I would do it like this, right? Indefine. I'd have the word return there because we don't indent it there. But just like we don't have the word start and then we don't start tabbing everything in the main code, right? I'm going to roll with it and I'm going to do it the way the book does it. Just know that this word would have to be indented or else it would be a syntax error if you did it in Python.
Mine's is orange.
Yeah, that's. Go ahead and put a triple quotes above it all, right? Because what's going on is it's actually trying to treat it as Python code and the return statement is orange. Okay, so I'm going to cut this stuff now and paste it into my real code. But it's all part of a comment, right? It's part of this, quote, quote, quote. Now, if I was going to turn this into real code, you know now that you'd have to put colons in the right places and change these to prints and add parentheses, and you'd have to tab that over. Colon there. Every time you start indenting, you have to have a colon. But we don't add the start word. You can put it in as a comment, and none of this stuff would be indented, just like it's not up here. I'm sorry for the differences. This is the way it goes. Pseudocode is generic. Doesn't follow not every language follows the specifics of it. I haven't seen any languages that have a start word and a stop word. Quite often they have a main up at the, Anyways, okay. Anybody need this slide up for a little bit longer? Or did anybody get a syntax error in the earlier part that you wish was fixed? Yeah, I'll scroll back up. Or do you need the feet and inches part? Okay. Define home. So.
Yeah, I'm right there. I'll put home.
Oh, did I need to scroll further for you?
No.
Are we good? Okay, yeah. So, a couple more lines for hum, but like this, right? Unless you're actually doing the code. I don't remember which part you're at.
Okay, I'm right there. I'll put.
Okay, okay, cool. But, all right. I'll briefly mention those again. So the module is called a subunit. I don't call it that. The book does. It's a subunit. Yeah. Some languages call it a subroutine. The basic programming language calls it a subroutine. Some languages call it a procedure. Some languages call it a function. Just about every language I teach calls it either a function or a method. A function is just like we showed, and a method is a function that's attached to data. Like our turtle program. When we said turtle dot forward, that dot forward was attached to a variable called turtle. That made it a method. That's a little picky. I'm not going to ask you what a method is. Just know that a function and a module are the same. To call a module is to use its name, causing it to execute. Notice that they use several terms. Call, They use the term invoke, right? Usually I will say call. Just know that invoke means the same thing. Runs it. So modularization is breaking down a large program into modules. I'm going to write the user interface that collects all the data from the user. And then you're going to write the part of the code that performs all the calculations. And then you're going to write the part of the code that displays it on the screen. And if we need to make it print a report, maybe we make a fourth module that's going to print it out to a printer. So, you know, we have 4 modules going on. And then some main code that controls it all. A very common programming model is called the view. Oh gosh, if I can't remember, I'm not going to confuse you. All right. The act of breaking it down is called functional decomposition. Decompose sounds bad, right? Like a body decomposing, but it just means breaking down. I'm not going to use that term after this. If it asks you on an exam, you know, one way to take the exam, the quizzes, is just to load up the PowerPoint, and if you see decomposition, right, Control F to do a search, right, decomposition, and then boom, you find it, right, and you go, okay, I see what decomposition is. Another thing you could do is you could copy and paste all of our notes into a single Word document. Because for the exam, I'm going to make a folder where you can upload stuff and you can stick all of your code and all your notes in it. Now, you can make it where you overwhelm yourself, right? But at least you'd have a good chance of being able to hit Control F and find out what, you know, I defined a module as, or what I meant by modulus, something like that. So abstraction. Modularization provides abstraction. Now, I read a book that every time the author meant distracted, they use the word abstracted. And it made me want to scream because I know what abstraction is, right? You know what abstract means, right? It's something theoretical, right? Well, this means something slightly different. But when you're doing something in abstract, you're not caring about the details, right? You're not plotting out every single little detail when you're thinking about something abstract. So abstraction is the idea that this module takes all of the details of asking the user for information, and then later on when I call it, I don't care about those details. I don't care how it's written. I don't care how the speed of light and the energy and the m, you know, E is equal to mc squared is calculated. I don't care, you know, whether, you know, what units it's done in or whatever, as long as it gives me the right answer. Now I've tested it, it gave me the right answer. I don't care about the details. When I call turtle.forward, I don't want to have to know how to draw a line going forward on the screen. That's a pretty complex process. Calling .forward makes it real easy. That's abstraction. Paying attention to the important properties while ignoring non-essential details. Well, they're essential to somebody, but I don't know how the turtle does it. I can make some guesses, right? It has to have an X position and a Y position and an angle that it's going and the color of the line and the speed of the line. But all of that is, you know, hidden inside the turtle. I have no idea. And here's a funny term, selective ignorance. That sounds bad. But I'm totally ignorant of how the turtle works inside it, right? And that's good, right? You don't want to know everything about everything. You can't know everything about everything. And so if you are able to take advantage of selective ignorance by using modules and libraries that people have created, that's totally good. The math library has sine and cosine and tangent. I don't know the formulas for calculating sine, cosine, and tangent. There are mathematical formulas for it, but I don't know them. I just want to be able to call sine. You know, the textbook told me to call sine. Great. So that's selective ignorance. So newer high-level programming languages use an English-like vocabulary. Now this is dumb because it's just kind of tucked in here about the definition of modularization. But this is important. One broad statement corresponds to dozens of instructions, just like a function, right? The computer uses that word while or if, but it has to turn it into machine code, kind of like we drew when we did chip, right? And he had all these numbers that he was following, all these opcodes. It could take a lot of different instructions to the chip to do one simple thing, like a print. And so, since we have the English-like vocabulary and the algebraic expression A is equal to B plus C, it's up to the compiler, it's up to the computer language to turn that into the machine language that controls the chip. So one broad statement does a whole bunch of machine language instructions, just like our functions, right? Singing did several different things. We could have made it do a whole bunch of things if it needed to be. So modularization allows multiple programmers to work on a problem. You can divide them up. Rarely does a single programmer write a commercial program, right? If something is being sold, it's probably not written by a single person. Okay, now is that completely false in some ways? Yeah. Lots of apps, right? If you're in the Google Store and the iTunes, you know, the App Store on your iPhone, yeah, you know, you have a single guy or a small, very small two-person team working on it, right? And you can make some money. The guy who programmed Flappy Bird made an obscene amount of money for that silly little program, right? Because it got incredibly popular. But usually, a complex program would usually not be written by a single programmer. Another example of that is what's known as the indie games, right? But it takes a person of an extraordinary amount of talent and will to write a PlayStation 4 game or an Xbox game. You know, the indie gaming movement, where you make a customized game that's a little bit, you know, different than one designed by committee, like the great big games you play, you know, Fortnite or World of Warcraft or whatever. So when you have a team, the software developers can write new programs. They divide the large program into modules, functional decomposition, and each module gets sent to a different programmer or team. You have some guys who are graphics specialists, and so they write all the graphics routines. We can reuse that work. The guys who wrote Quake, for example, a game a while back, first-person shooter, made huge amounts of money, more money than they did from that game, by licensing those functions to other people to make their own games. So that was called the Quake engine, the engine being a whole bunch of functions that they sold for other people to use, which allows the reuse. And reliability. Nobody would use the Quake engine, the Quake functions, if they caused it to crash the computer. So those modules were tested and debugged, and then if I bought them from the guys who created it, then I would have some good sense that they were reliable. If they were not, you know, you get on the internet and you complain, or you know, you demand your money back, whatever. You hope that the modules work. Not only do you hope that they work, you do some testing to make sure they work. But if you know, once they are proven to work, then you can rest kind of comfortably on it. So modularizing a program, the main program, that's the basic steps of the program. You include what's known as the module header, the module body, and the module return statement. What is the module header? The module header is just a definition. It might take a variable like that, right? And then it might use that variable. Well, that's the header, and it's got a parameter. Yeah. And it's got a return statement. So the header, the body, and the return statement are the three parts of a module, the three parts of a function. So when you name a module, you want to give it a good name. It'd be absurd to give a function a one-letter name. You could, or you could call it Fred, right? But it's better to give it a good name. Calculate velocity, calculate density, you know, get average, whatever. And when you define your module, it's followed by a set of parentheses. And if that module needs any variables that are passed to it from outside of it to work, then you put that inside the parentheses. All right, now we're going to try to do a real program. I don't want to run out of time, but I think we could draw this in about 15 minutes. So let's give it a shot. We're going to write a program that uses E equals mc squared to convert energy, to convert mass into energy if it was traveling at light speed or something like that. That's even more energy than if it was vaporized in an atomic bomb. So anyways, let's come back over here. And here's what our program is going to do. So I'm going to define a module called calc energy. Give it a kind of a good name, but I need a constant first for what c is. C is the speed of light in mc squared, and you don't care about the details. I just give you this formula and you use it. Speed of underscore light, you can always Google it, hit Wikipedia if you're curious about what this really works, is equal to 3e6. Speed of light equals 3e6, and I'm going to put a comment of the units, meters per second. That's the only constant I can think of. So we're going to write the formula. Define calc underscore energy. This particular module needs a piece of data. It needs a number of kilograms. So inside the parentheses, I'm going to declare what's known as a parameter variable. kg is parameter variable, usually just called a parameter. And so energy is equal to the mass, the kilograms, times the speed of light squared. I'm just going to copy the word speed of light and paste it because I'm lazy and I don't want to make any typos. So E equals kg times, paste that, and then type star star 2. It's squared. And then we need to return that energy so the calling code can use it. Now we want to ask the user for the energy. Excuse me, the mass. So I could put a start comment here. Don't have to. We're going to input the amount of kilograms. So kilograms equals input, parentheses, quote, what is the mass in kilograms, question mark, end quote, in parentheses. Now we need to turn it into a number. kg equals float, parentheses, kg. I should have pseudocoded this out first. All right, now I'm going to find out the energy. Energy equals calc underscore energy, and in parentheses, passing kg in. When I pass it in, that's called an argument. When it gets up here, it's called a parameter. So I'm going to add that as a comment. kg is the argument that fills in the parameter. Those names are so close. I mean, those concepts are so close that a lot of people interchange them, right? All right, kg is my parameter. I'm passing in 3 parameters. No, you're passing in 3 arguments, and it fills in the, Technically, this is the parameter when it's in the definition, and this is the argument when it's being called. All right, now we have the energy. We can print it out. Print, parentheses, quote, by E equals MC2, comma, that is, end quote, comma, energy, comma, quote, joules, because that's a unit of energy that it measures. And now we're done. Stop. If I was going to do this as pseudocode, it would look like this. I might skip the definition up here. I might. Probably not. But I'm going to wind up skipping the definition in the flowchart because I don't know how to do that, honestly. So I guess I could define it inside the function. That would make sense. So anyways, we would define calc underscore energy, which takes a parameter, kg, in parentheses, colon. It sets this value, E equals kg times speed of light, except this is pseudocode, so I'm going to stick the word set in front of it. And then we return E. That's our function. And I know I'm going a little bit fast because I want to draw this as a flow chart. I'll be happy to print this out so that you can finish entering it on your own time if you want. And then we have the start and the stop. So start, stop, energy or set energy equals calc underscore energy parentheses kg in parentheses. And then output energy. That's good enough. I'm not going to make it all complicated, except I forgot something. What's the difference between my code here and my pseudocode if you've already typed in everything? Do you see a problem? I left out something. What was the very first step under the word start? I think I heard it. Be assertive, guys. What's the first? Yeah, the input statement. Okay, so this should have been input kg right there. And I know I've left y'all behind, some of y'all. So like I said, we're going to go ahead and do the flow chart, but then I'll come back and leave this on the screen or print it out for you. So here we go. Go to Lucid Chart if you're going to draw it along with me. Don't have to. Log in if you gotta. Make a new document. The first thing you got to decide is what you're going to put in the first column. I like putting the functions and then the main code later, right? Just because that's how we write it in pseudocode and Python. We define them first. I happen to have this memorized, so I'm not going to keep the code on the screen, but I should copy and paste the code. So this is the start, except it's not the start. This is a function. This is define calc underscore energy. Parentheses in parentheses, but inside the parentheses it takes a variable. It takes the parameter, which is kg. And I'm going to hit Control Enter, Command Enter, just to make it look like that. Then I'm going to come down here, and this is a math statement, so it goes in a rectangle. Set E for energy equals the kg times speed underscore of underscore light to the power of 2. Then a return statement, return E, goes in another oval. And like I showed you before, I like colorizing the functions, so I'm going to click on def energy and use the paint bucket to pick a color for it. Now the main code, the rest of it begins with a start oval, start terminator, a start sentry, as the book calls it. Start. We input the kilograms, we call calc energy, we output the joules. So input is done in tilted. So input kilograms. I'm going to make that box kind of smaller. And then I'm going to call the function. So I'm going to have E, or energy, equals calc energy, parentheses kg. But it's a function call, so it needs the rectangle with the vertical bars. So energy equals calc underscore energy, parentheses kg. I could put the word set in front of it if I wanted to make it match the pseudocode. I don't care if you use the word set or not. I consider it optional. The next one's going to be output energy. What shape does output go in? Tilted rects. Data block. Output energy. And then the stop is the oval. All right. Just to make things nice, I'm going to go ahead and copy the pseudocode and paste it into my flowchart. I don't care if you do this. I'd kind of like for you to do it on your homework, though. So I'm going to grab a box. I'm going to paste my code in there, and then I want to left justify it. How do I left justify it? I come over to alignment. Well, it only did one line. I better highlight it all and then left justify it. Come over to alignment, which is next to the T in the toolbar. Stretch this out. Maybe add a control return or a command return. All right, that's my program, or that's my flowchart. But I told y'all I like colorizing, so I'm going to make the call to calc energy blue. So I'm going to use a paint bucket to make it blue. So guess what I'm going to do? I'm going to give y'all some pseudocode, and I want you to draw a flowchart for it. Some people are speed demons, and so they're probably done drawing the flowchart. I'm going to create the Dropbox for this, show you the homework, and then leave the pseudocode and the flowchart on screen or print them out for you. Yeah, save your flowchart. Just call it, I guess we're on G. Call it G or EMC using an EMC squared. Okay, anyways, I need to get this going. Where's the homework assignment? The homework assignment is over here inside the other box. I'm going to change it a little bit, though. I'm not going to ask you to code it in Python, which I asked the other folks to do. All right, so homework 4 is to draw a flowchart, but not implement it in Python. And the logic shows how to calculate overtime, right? You work 50 hours a week, you get 10 hours of overtime if you have that kind of job. So here's the pseudocode for it. It's got 2 functions. You do them the same way you do one function. So define get hours. Then you input the hours and you return the hours. That's the first function. And then define the rate. Input the rate and return the rate. And then here's our program between the start and the stop. Right? We're going to ask the user, how many hours did you work this week? And then we're going to ask the user, what's your pay rate? And if the hours is greater than 40, then we calculate a bonus. And that formula is wrong. I better fix it. I better fix it for the other team now. Else, if they didn't work more than 40 hours, the bonus is 0. Then the pay is equal to, right, 50 hours times $10 an hour or whatever you earned, but then you can get a bonus if you worked overtime. And then you output that total. And you don't have to do any special things about, you know, conversion and printing, you know, what you're inputting and stuff like that. If you're writing Python, you'd want to, but for the flowchart, I don't care. All right, that makes sense? Just calculating. Yes,
What
sir.
about the overtime? You said that was wrong, bonus equals.
Oh, I have to fix this equation. Let me fix it while we're even looking at it. That was dumb. No, I think that's correct. It could be written in one line of code, but I'm going to leave it in 2 lines of code. Just use 2 rectangles. It's actually correct. All right. Make the drop box and come back. I'll print out anything anybody needs. I'll hang out for as long as y'all need.
Can you put it back on the flow chart?
Just a sec. Making a drop box. All right, if you refresh your assignments, there's a box G. All you need to do is save your flowchart, file save, and then do file download as always. All right, you needed to see the flowchart?
Yeah.
Here we go. Who would like a printout of the code because you didn't type in the code while I was doing it? All right, I see 3 hands raised. 4. No problemo. Yeah. This part? Well, I'm going to print out 4 copies.
Yeah, I need one too.
All right.
I'd like you to, please.
All right. My pleasure. Back to the flowchart. Just say